Hey everyone, and welcome back to Talk Tensors. Today we're diving into this paper that's really making waves in the world of LLMs.
Oh, yeah.
Yeah, like it's tackling this
Okay.
ever so tricky question of control. How do we make these powerful models behave the way we want them to?
Right, right.
I mean, we've all been there, right? Wrestling with fine-tuning, that seems to take forever.
Yeah.
Or trying to coax the right output just from prompting.
Yeah, for sure.
Like, what if there was a better way?
Right.
A more precise and interpretable way to steer these LLMs?
Well, that's precisely the question that this paper sets out to answer.
Okay.
AxBench stage, steering LLMs, even simple baselines outperform sparse autoencoders.
Wow, that title really caught my eye.
Really?
It's like a bold challenge to the entire field of representation learning.
Yeah, it is.
So can representation steering really stand up against those tried and true methods of prompting and fine-tuning?
Well, the paper really puts these methods through their paces, testing them on two key tasks. One is concept detection. Can we actually accurately identify the presence of a specific concept in the text?
Gotcha.
And then the second one is model steering.
Okay.
Can we actually change the model's output to include a concept or exclude it?
Interesting.
And here's the kicker.
Okay.
They found that even simple baselines sometimes outperform those more complex representation-based approaches.
Hold on, so we're talking about potentially simpler and more efficient ways to control these LLMs.
Potentially, yeah.
Okay, now this is piquing my interest. Tell me more about this AxBench, this new benchmark that they're introducing.
So AxBench is all about creating a level playing field for evaluating these different steering methods.
Okay.
And they achieve this by using synthetic data. This allows for a much cleaner and controlled experiment.
So synthetic data, meaning they're essentially creating like artificial text to train and test these models.
Exactly.
Interesting.
They start by feeding AxBench here a list of natural language descriptions of concepts, sort of like giving it a vocabulary list of ideas to work with.
Got it.
Then AxBench takes these descriptions and uses them to generate a whole mountain of synthetic data,
Okay.
both for training and for testing.
So it's like creating a custom-made training ground for these models.
Precisely.
Okay, cool.
Well,
So they don't just generate simple examples, I'm guessing.
No, they don't. They have a three-pronged approach.
Okay.
So they create these positive examples, right? So that clearly contain the concept. They also have negative examples, which are completely unrelated. And then they have hard negatives.
Hard negatives. Those sound particularly tricky. What are those all about?
Yeah, so hard negatives are designed to be real brain twisters for the models.
Okay.
They involve concepts that are semantically related to the target concept, but they shouldn't be triggering the model to think about that concept. It's like saying, you can talk about bridges in general, but don't you dare mention the Golden Gate Bridge specifically.
So it forces them to really hone in on their understanding and be super precise.
Yes, exactly.
Oh, wait, didn't you say they use another LLM to generate all this data?
They did, yeah.
So it's like AI inception?
It is, and that's one of the things that makes this benchmark so interesting.
Okay.
They're using the power of one LLM, in this case, GPT-4 Mini, to evaluate the controllability of others.
Okay, so they got this synthetic data covering a range of text types, regular text, code, even math.
Yep.
That's quite a diverse set of challenges.
Absolutely. And testing these methods across such a diverse range makes the benchmark much more comprehensive and representative of real-world applications.
Okay, so we've got our training ground.
Right.
And we've got our diverse set of challenges.
Yeah.
Let's dive into the first task, concept detection. How well do these different methods actually perform at spotting those target concepts within the text?
So they put a whole lineup of methods to the test, from simple statistical approaches like difference in means to more complex representation-based methods like sparse autoencoders, or SAEs for short.
Wow, that's quite a range of techniques. I'm guessing each one takes a slightly different approach to finding those concepts.
Exactly.
Okay.
Let's start with the simpler end of the spectrum.
Okay.
Difference in means, as the name suggests, simply looks at the average activation of neurons when processing text that contains the target concept versus text that doesn't.
Correct.
If there's a significant difference, it suggests those neurons are sensitive to the presence or absence of that concept.
So it's like a simple but intuitive way to see which parts of the model light up when they encounter the concept.
Exactly.
Okay, so what else? What other methods are there?
Then we have principal component analysis, or PCA. Imagine all the text representations as points in space.
Okay.
PCA essentially tries to find the line that best separates the points representing texts with the concept from those without. It's like drawing a dividing line through that cloud of data points.
So PCA is all about finding the direction that best captures that distinction between the concept and everything else. What about some of the other methods?
Another interesting one is linear artificial tomography.
Okay.
Now, this method gets its name from a medical imaging technique, and it takes a slightly different approach.
Okay.
Instead of looking at the average activation, it focuses on the differences in activation patterns
Okay.
between different texts containing the concept. It's like trying to reconstruct an image from multiple projections, but in this case, we're reconstructing the concept from different activation patterns.
So it's trying to extract the essence of the concept from how the model responds to those different examples.
Yeah, that's a good way to put it.
That's pretty...
With supervised steering vectors. These vectors are designed to specifically nudge the model towards generating the target concept.
Okay.
Essentially, they learn a direction in the model's activation space that, when added to the input, makes it more likely to produce text containing that concept.
So instead of just detecting the concept, we're now actively trying to steer the model's behavior.
Exactly.
Got it. So lastly, we have those sparse autoencoders.
Right.
Those super dictionaries for neural networks.
SAEs are all about finding compact and meaningful representations of concepts.
Okay.
Imagine taking a complex idea and breaking it down into its essential building blocks. That's essentially what an SAE tries to do, but instead of words or phrases, it's using these high-dimensional vectors of numbers.
Okay.
They learn to represent concepts in a way that's both sparse, using as few components as possible, and accurate.
So it's like distilling the concept down to its purest form within the model.
Yeah, I like that.
Okay, we've got our contenders. What about the results? Were there any surprise winners or losers in this concept detection challenge?
The results were actually quite revealing.
Oh, yeah.
Yeah. The big surprise was that the simpler methods,
Okay.
like difference in means, linear probing,
Okay.
and rank 1 representation fine-tuning, or ReFTR1, actually performed the best.
So the underdogs took the lead.
Kind of, yeah.
That's unexpected. I would have thought the more complex methods would have the edge.
Yeah, you'd think so, right?
Yeah.
But it turns out, for this task at least, simplicity reigns supreme.
Okay.
And what's even more interesting is that these simpler methods held their own,
Okay.
even when the data was intentionally imbalanced.
Imbalance of data. What does that mean?
So in real world, text concepts don't appear with equal frequency. Some are common while others are rare.
Right.
And this imbalance can trip up some machine learning models, making them less accurate. So the fact that these simpler methods performed well, even with imbalanced data, suggests they're more robust and potentially more generalizable.
Okay, so this finding has implications beyond just this particular benchmark.
Right.
It could point to a more fundamental truth about how these LLMs represent concepts.
Yeah.
So what does the effectiveness of these simpler methods tell us about the way these LLMs store and process information?
Well, that's a great question.
Yeah.
And it's one that researchers are still exploring.
Okay.
One possibility is that the key concepts that the model needs to grasp for tasks like concept detection are actually encoded in relatively simple and accessible ways within the model's activation.
Okay.
This could explain why these simpler linear methods are so effective. They're able to tap into those core representations without getting bogged down in the complexities of the full model.
This raises a fascinating question. If these simpler methods are so effective, do we really need to go down that more complex path of SAEs for concept detection? Could there be a sweet spot, a way to combine the efficiency of these simpler methods with the representational power of more complex approaches?
Absolutely. And this is where the distinction the paper makes between supervised dictionary learning, or SDL, and self-supervised methods like SAEs becomes really important.
Okay, let's unpack that a bit. What's the key difference between those two approaches?
Think of SDL as a more targeted approach.
Okay.
Methods like difference in means and ReFTR1 fall into this category.
Okay.
They need to know the concepts they're looking for beforehand. They're essentially given a dictionary of concepts and trained to find them within the model's representations.
So it's less about discovering hidden features and more about precisely identifying what you're already looking for.
Precisely.
Okay.
And the trade-off is pretty clear.
Mm.
SDL might be less flexible
Okay.
than self-supervised methods like SAEs, which can learn representations without explicit labels.
Right.
However, SDL is also much cheaper to train and potentially more effective
Okay.
if you have a clear set of concepts that you're targeting.
This begs the question, could combining SDL with better concept labeling techniques lead to even more powerful and efficient steering methods?
Potentially, yeah.
Imagine a system that can automatically identify and label those key concepts within a text, and then use those labels to train an SDL-based steering model.
Now you're thinking ahead.
Yeah.
That's a very promising avenue for future research.
Okay.
And it really highlights the potential of combining these different approaches to leverage their respective strength.
Right, let's shift gears now.
Okay.
And talk about that second challenge.
Yeah.
Model steering.
Right.
This is where we're not just identifying concepts, but actually trying to manipulate the model's output to include or exclude them.
Right.
So how did the different methods fare on this more active task?
So for model steering, they used a clever evaluation approach.
Okay.
Another LLM was employed as a judge to rate the outputs generated by the different steering methods.
So using another LLM as a judge, that's an interesting choice.
It is.
It's like having a panel of AI experts evaluate the quality and relevance of the generated text.
Right.
But what are the potential limitations of this approach? Could the judge LLM have its own biases or limitations that might affect the evaluation?
That's a very valid point.
Yeah.
The choice of the judge LLM is crucial,
Right.
and its limitations could indeed influence the results.
So,
It really highlights the importance of carefully considering those evaluation metrics and making sure they align with the desired outcomes of that steering process.
so how did the different steering methods perform under the watchful eye of the judge LLM? Were there any surprises in the model steering task?
The results from model steering were a bit more in line with what you might expect, with one notable exception.
Oh.
As you might have guessed, prompting emerged as the clear winner.
Well, prompting is essentially telling the model exactly what you want.
Exactly.
So it's not surprising that it would excel at this task.
Right. It's the most direct and explicit way to steer the model's output.
Yeah.
However, fine-tuning methods, while more resource-intensive, came in a close second.
Okay.
And this is where things get interesting. Remember re-FTR1?
Yes. The overachiever of the group.
That's the one.
Yeah.
Well, it continued to impress in the model steering task as well,
Oh, wow.
particularly when tested on smaller language models.
Okay.
It was the only steering method that came close to the performance of prompting, even outperforming some of those more complex fine-tuning approaches.
So re-FTR1 is proving to be both efficient and surprisingly effective.
It is.
It makes you wonder if we've been overcomplicating things in our quest to control these models.
Yeah, possibly.
What about the SAEs? How did they perform in the steering task?
Unfortunately, the SAEs, even with careful feature selection, lagged behind the top performers in the steering challenge. They struggled to match the precision and controllability of prompting, fine-tuning, and even the simple re-FTR1 method.
Okay, so this discrepancy in performance between concept detection and model steering, that raises some important questions
It does.
about the nature of representation steering and the trade-offs involved in those different approaches.
Right.
It leads us to a crucial point. Understanding those different approaches to controlling LLMs and their respective strengths and weaknesses.
Yeah.
So we've talked about prompting, fine-tuning, and now representation steering. Can you maybe elaborate on the trade-offs between these approaches and what this research suggests about their future?
Absolutely. So prompting is like giving the model very specific instructions.
Okay.
It's quick and easy, but it can be hit or miss in terms of getting that desired output. Fine-tuning is like retraining the model for a specific task,
Okay.
which gives you more control, but requires a lot more data and computational resources.
Gotcha.
So representation steering kind of sits somewhere in between.
Okay.
It aims to be more precise
Okay.
and interpretable than prompting, and less resource-intensive than fine-tuning.
So representation steering is like finding the right levers to pull within the model.
Yeah, that's a good way to put it.
Yeah, to guide its behavior in a more nuanced way.
Right.
But as this research shows, finding those levers and learning how to pull them effectively, that's still an ongoing challenge.
It is, definitely.
It sounds like we're still in the early stages of understanding how to effectively steer these powerful models.
I think so.
But this research provides some really valuable insights.
Yeah,
And it opens up some exciting avenues for future exploration.
for sure.
Speaking of exploration, let's move on to one of my favorite segments,
Okay.
novel notions.
I like this part.
Yeah. So, inspired by this paper and its findings,
Right.
what are some concept teleportation? Are we beaming concepts from one LLM to another?
Precisely.
Wow. Okay.
Imagine we train a model that can directly translate those SDL features, those steering levers we've been discussing, from one LLM to another.
Okay.
This means we could transfer those steering abilities without having to retrain everything from scratch for each new model.
That's a fascinating idea.
Right.
We could take a feature that steers one LLM to discuss, let's say, climate change solutions,
Right.
and instantly apply it to a different LLM, even one with a completely different architecture.
Exactly.
This would revolutionize the development and sharing of steering techniques.
It would.
Imagine a world where we can rapidly adapt steering techniques to new LLMs as they emerge. This would greatly accelerate the pace of research and allow us to harness the power of these models for a wider range of applications. But hold on a second. While that sounds incredibly promising, how do we guarantee that these translated features will work reliably in a different LLM? What about the potential for errors or unintended consequences?
You bring up a critical point.
Yeah.
Ensuring the accuracy and reliability of those translated features, that would be a major challenge.
Oh, yeah?
It would require a deep understanding of how different LLMs represent concepts and how to map those representations effectively across those different architectures.
So while concept teleportation is a tantalizing idea, there are significant hurdles to overcome.
Definitely.
Sounds like we need a deeper understanding of the inner workings of these LLMs before we can start beaming concepts between them.
Yeah, good point. The possibilities are truly mind-boggling. But
Yeah.
let's take a step back for a moment and consider the broader implications of this research.
Okay.
What does this tell us about the nature of intelligence, both artificial and human?
That's a profound question. It seems like we're grappling with these fundamental questions about control, understanding, and perhaps even consciousness as we delve deeper into these models.
Exactly. This quest to control LLMs forces us to confront the very nature of intelligence itself. What does it mean to understand a concept? How do we represent knowledge and reasoning within these artificial systems?
Okay.
And perhaps most importantly, how do we ensure that these systems remain aligned with human values and goals as they continue to evolve?
These are questions that extend far beyond the realm of computer science.
Absolutely.
They touch upon philosophy, ethics, even our understanding of the human mind.
Absolutely.
Yeah, and that's what makes this field so fascinating and so challenging.
It is.
We're not just building machines, we're exploring the frontiers of knowledge and grappling with questions that have puzzled humanity for centuries.
Right. It's both exciting and a little bit daunting.
Yeah, I agree.
But I think it's crucial that we have these conversations.
That we bring together these diverse perspectives from different fields to ensure that the development of AI is guided by wisdom and foresight.
I couldn't agree more. The future of AI is not something that should be left solely in the hands of technologists.
I agree.
We need a collective effort involving ethicists, philosophers, social scientists, the public at large, to shape the development of these powerful technologies in a way that benefits all of humanity.
Well said.
This deep dive has certainly been a journey.
It has.
Taking us from the nitty-gritty details of representation, steering to the broader implications of AI and its role in society.
It's been a pleasure exploring these ideas with you.
Likewise. And to our listeners, thank you for joining us on this exploration of LLMs and the quest for control.
Yeah, thanks for listening, everyone.
As always, we encourage you to check out the paper itself. The link is in the description below.
Yep.
And if this episode has sparked any novel notions of your own, we'd love to hear them.
Definitely.
Until next time, keep those minds curious.